Hello everyone, so now I'm going to move on to something very important in calculus, which is called logarithmic differentiation. Right, so what do we mean by that? When we say logarithmic differentiation, we mean the use of possibly logarithm rules, logarithm identities, and our knowledge of the exponential function in order to differentiate. And that mostly applies to implicit differentiation, so you can kind of see why I decided to make this video after I cover implicit differentiation. So there's quite a bit of formula here, and obviously there's this lovely quote by Dr. Sarkis: when you can prove that the derivative of a natural logarithm x equals 1 over x, that's when you know, or that's when you can be assured that that the calculus spirit is within you. So actually what I mean by that is that if you know logarithmic differentiation, then you're probably good to go with starting integrals, because it's not too easy. So we know that the derivative of e to the power of x is e to the power of x, and partly that's because the derivative of e to the power of kx equals k times e to the power of kx, and if k equals 1, then you end up with what he started with, which is basically e to the power of x. And then we have some rules of conversion when you convert between logarithms, and that's basically just never mind. Well, and this, but those three rules are probably the most important here. This rule is also kind of important, but we will discuss this later in a different video, so in more depth. So what you need to know for now is that the derivative of e to the power of x equals itself, and that the derivative of the natural logarithm of x equals 1 over x, which is very elegant. It's one of the most impressive results in calculus. But now what I'm going to do is, I'm going to try and show you why this is the case, give you the intuition. So suppose we are trying to find the derivative of the natural logarithm. In fact, this is what we're trying to do. So y equals the natural logarithm of x. How can you use implicit differentiation in order to do that? Well, one thing we can do, which is very interesting, is in logarithmic differentiation, we can take everything to the power of e. We can either find the natural logarithm of all the results here, which wouldn't really be helpful here, or we can raise everything here from both sides, to both the right hand side and the left hand side, to the power of, so from the base of e, so e to the power of y equals e to the power of ln of x. Now e to the power of ln of x is like the same thing as take e and raise it to the power of whatever takes e to x. So that's basically going to give you x. So x is going to be here, is going to be e to the power of y. And then what we can do now is we can differentiate both sides. And what we get is we will get the derivative with respect to x of x, or square brackets, it doesn't really matter, equals the derivative here with respect to x of e to the y. And because this is a function of y, we're going to end up here with 1 equals, exponential functions stay the same. It doesn't matter if it's x or y, but because it's a composite function, y is a composite function of x, you're going to use the chain rule, and that's going to give you the same thing times the derivative dy over dx. And now if you want to find dy over dx, dy over dx is going to be equal to 1 minus e to the y, right? But what is e to the y? We said that y is the same thing as ln x, right? The natural logarithm x, which means the logarithm with a base of e. So a logarithm, if you haven't told you yet, is just and it's probably quite useful to make it clear now. Logarithm is a function which takes a base, which takes two inputs. It takes a base and it takes a value, which you're trying, an anti-logarithm, a value you're trying to find, which power gives you that. So if I tell you what is the logarithm base 2 of 7, that just means I want this function to work out which power of 2, so 2 to the power of what, gives me 7. So that using that logic, that just means we're doing 1 over e to the power of ln of x, and using that rule, e to the power of ln of x is the same thing as e to the power of whatever turns e to x. So that's just going to give you 1 over x, and we are done. And we have fulfilled the purpose of the lesson here, because when you can prove that the derivative of the natural log of x equals 1 over x, that's when you know that the calculus spirit is within you, because it is quite possibly not very intuitive. It definitely does get easy as you move on to integrals, but for somebody who just kind of got the basic understanding of the chain rule and can now do that kind of stuff, if you can understand this, then you're good. Okay, so before I move to the next video, I just want to give you an intuition for possibly, I'm not going to show you a proof because that's going to be overkill, right? But I'm going to show you that the derivative of a to the power of x is the same thing as e to the x times the natural logarithm of a. Yeah, I'm not going to show you a proof, but I'm just going to make you think about things in this way. So a is just a number, right? And e is just a number, right? So it makes sense that this is the case, because imagine if a equals e. What do we have then? We have, the answer here is e to the power of x, e to the x, times the natural logarithm of a, so a is equal to e. And the natural logarithm e is, again, what power of e gives you e, and for any number, what gives itself is essentially 1. So 1 times e to the power of x, e to the power of x is equal to e to the power of x. So that's quite interesting. I think I'm probably going to make another video on logarithmic differentiation, but for now we're going to end this video, and I might make a video focusing on some of those formulae more in depth, although you don't often get logarithm questions in calculus unless it's the natural logarithm. So I doubt I'll make extensive use of change of base and all sorts of other tricks of logarithms. So see you in the next video.